Today we study chapter 6, two topics from 6.1. The first topic, polynomial interpolation. The second topic, different methods to find interpolating polynomials. Chapter 6 is about approximating a function with a relatively simple function. The simple functions in this chapter are polynomials, sprite functions, and continued fractions. But we only focus on polynomial and sprite functions. We don't touch continued fractions. Temporarily, we skip chapter 4 and chapter 5. Chapter 4 and chapter 5 are about the solution of linear systems. At the end of the semester, if we still have time, then we go back to chapter 4 and chapter 5, but not now, okay? The problem that we want to solve in this chapter 6, is this problem. Suppose we are given some data points about function f. Say here, it is a table about n plus 1 data points. We want to find a polynomial. Let me call that polynomial P. This polynomial, the degree as lowest as possible, such that P is polynomial passes through all the data points. This is the problem that we want to solve. There are two cases about function f. If function f, we don't know it, then we consider this polynomial recovery of function f. Situation 1. The second situation is, if we know the function, then this polynomial is considered to be an approximation of the function f. So, two situations about function f. If we don't know f, then P is a recovery of function f. Reconstruct function f. If we know function f, then P is an approximation of function f. Okay, now we want to solve this problem. Given a table of some data, find polynomial passing through all the data points. There are two theorems in this section 6.1. Let me present the first one, the first theorem. Before I present the two theorems, let me introduce some terminologies. Number 1, a polynomial that passes the given data points is called a polynomial that interpolate that interpolate the data. Second terminology, let me see. A polynomial that passes the given data points is called a polynomial that interpolates the data or interpolates the function f at the loops x0, x1, xn. Yeah, the x values in the table are called loops. Usually, these points are different, distinct to each other, usually. The second terminology is, let me see, the process of seeking a polynomial, a P, that satisfies the given data. Okay, this process is called a polynomial interpolation. Here in section 1, we use polynomial to pass through all the data points. If we use sprite functions, yeah, here I mentioned sprite function here. If we use a sprite function to pass all the data points, then the process is called a sprite interpolation. If we use continual fractions to pass all the data points, then the process is called continual fraction interpolation. Okay, now let me present the two theorems in this section. The first theorem, to prove interpolation polynomial always exists. Theorem number 1. Suppose the loops are x0, x1. X1, x2, xn are distinct to each other. They are different. Of course, real numbers. Okay. Then for any y0, y1 function values, there is a unique one and only one polynomial. P, I call the polynomial P of degree at most less than or equal to n. Yeah, n plus 1 data points. The lowest degree of interpolation polynomial is n. Is n. There is one and only one polynomial whose degree is not greater than n, such that the polynomial satisfy all the data points. That means that function value, polynomial value, and the ith root is equal to yi. Okay. What is I? I is from 0 to n. Satisfy these conditions, one and only one polynomial. Okay. How to prove this theorem? The proof not difficult. The proof. I can write. Let me write the polynomial as the constant term is a0, and then the term associated with x is a1. Associated with x squared is a2, and so on. Degree is n, an. Yeah. When an is 0, the highest degree term is 0, then the polynomial, the degree less than n. When an non-zero, then this polynomial, the degree is exactly n. Okay, now I assume this polynomial satisfies these conditions. These n plus 1 conditions. Now I plug in the roots in x. Okay. Then I plug in x0 in x. I have this equation. I plug in x1 in x. I have this equation, and so on. Xn, yn. Yeah. Yeah, these n plus 1 conditions are from here. All right, now in detail, polynomial at x0 is I plug in x0 in x. Then I have one equation. X0 plus a2 x0 squared an x0 squared is equal to y0. Second equation, a0 plus a1 x1 plus a2 x1 squared an x1 1 to the n, the power is n y1. The last equation is a0 plus a1 xn a2 xn squared an xn to n yn. We have a system of n plus 1 equations. How many unknowns? The coefficients are unknowns. How many? M plus 1 unknowns. So M plus 1 equations, M plus 1 unknowns. The solution should be unique under some condition. Let me write this linear system in matrix form. Okay, in matrix form. In matrix form. The coefficient matrix is a 1, x0 squared, and so on, x0 to n. The second row of the coefficient matrix is a 1, x1 squared, x1n. The third row, x2 square, xn, x2n, x2n, and so on. The bottom row, 1 xn, xn square, xn to n, coefficient matrix, times the vector of the unknowns. Unknowns are coefficients, A0, A1, A2, AN. The right side of the linear system, the right-hand side is function values at the roots. It is y0, y1, y2, yn. This linear system has only one solution. Why? The coefficient matrix of this form, actually, we have a name for this matrix. It is Vandermonde. Vandermonde is the name of a mathematician. Vandermonde matrix. Let me denote this matrix by, say, by A. Say by A. Denote it by A. Then it is well known. Determinant of this matrix is equal to x0 minus x1 times x0 minus x2 times x0 minus x3 and so on. x0 minus xn. Okay, times now x0 now x1 minus x2, x1 minus x3 and so on. x1 minus xn, and times x0 x1 now turn to x2 minus x3, x2 minus x4 and so on. x2 minus xn. Okay. The product of the difference of different roots. x0, x1, x2. Now this is xn minus 1, xn minus 1 minus xn. Because we assume in this theorem, we assume the roots are distinct, they are different. So this product non-zero. Right? x0 minus x1 non-zero, x0 minus x2 non-zero. So the product is non-zero. Right. So in other words, when determinant is non-zero, matrix A is invertible. Invertible. Matrix A has inverse. So therefore, this linear system has only one solution. There is one and only one solution, because I can move A to the right side by taking inverse on A to get the solution. Yeah, this is the proof of the theorem. Because the coefficient matrix is invertible, therefore solution is just one. Okay, that's the proof. So this theorem says that interpolation polynomial is one and only one. Okay. The lowest degree polynomial is one and only one. Yeah, this theorem is about the existence of interpolation polynomial. Now the second theorem is about error. We are approximate a function by a polynomial. Then what is the error between these two functions? Error, the difference, error. Okay. Now, second theorem. Theorem 2. This theorem is on polynomial. Interpolation error. Yeah, the proof of this theorem is skillful. Okay, is skillful. I suppose function f is in this set. This notation means all the functions defined on the open interval AB, and those functions have derivative up to n plus 1. N plus 1. You can take derivative n plus 1 times. Let me see. Here, not n plus 1. Let me erase. N is the number of the roots. No, here is not n. How about I use m? M and n different. And then P be the polynomial of degree not greater than n. Then from theorem 1, this polynomial we know that exists and is unique. The polynomial P interpolates function f and the n plus 1. Pay attention, this n and this m different. Distinct looks x0, x1, x2, and xn. These roots all are in the interval AB. In the interval AB. Okay, now conclusion. Then to each x in the open interval, x any point from the interval AB, there is a point, a sign depends on x. This point is also in the open interval AB, such that the function at x minus polynomial at x is equal to 1 over n plus 1 factorial. Yeah, the error term similar to the error terms in Taylor's theorem. F take derivative n plus 1 times, then evaluate at the point psi x. Then times, yeah, very similar to Taylor's theorem. I from 0 to n, x minus xi. Yeah, this is the error term about polynomial interpolation. Yeah, actually, we often use this theorem. Now, then, how to prove? The proof is interesting. Okay, and okay, let me divide the proof into two cases. Case one. X is any point in the open interval. X is one of the lobes. The lobes, yeah, we call x0, x1, x2, xn are the lobes. If x is one of the lobes, then this polynomial is true. It is easy to see that. Okay. The left side. Let me see. The left side of equation 1 is x is one of the lobes. Say, suppose, without loss of generality, x is x0, for example. Then the left side is f x0 minus p x0. Okay, f of x0 is y0 from the table. Yeah, the table here. Yeah, from this table. When function value at x0, the value is y0. Here I assume P interpolates function f at the lobes. That means that polynomial its value at x0 is also y0. So left hand side is 0. How about the right side? The right side of equation 1. Yeah, this equation. I plug in x0 in x. F m plus 1 sine x0. Actually, in this case 1, sine can be any point. Now the product is let me expand the product. When I is 0, x minus x0, but now x is x0, so x0 minus x0. Now the second factor, when I is 1, x minus x1. Now x is x0, so x0 minus x1, and so on. x0 minus xn. But the first factor is 0, so the whole product is 0. Yeah, this is 0. So in this case, if x is one of the lobes, left side is equal to the right side. No problem. Now, second case, x is different from the lobes. Case 2. X is different from the lobes. Okay, from the lobes. Okay, now okay, let me introduce this function. These functions, okay. Wt, t is a variable, is equal to t minus x0 t minus x1, t minus xn. Okay. First function, I define some new functions. First function. Okay, now the second function is phi t is equal to function f at t, then polynomial at t. This polynomial is interpolation polynomial. Then minus lambda times wt. Wt is defined here. Wt is defined here. All right. In the second case, the proof we hold x fixed. X is a fixed number, not a variable. The variable now is t. Okay. W is a polynomial in t. Degree. This is a polynomial in t. Degree. What is the degree of this polynomial? How many factors? First factor, second factor, n plus one factor. So the degree is n plus one. Yeah, n plus one. Okay. Now here, what is lambda? Where lambda is a constant. Which constant? Okay. Function value at x. Remember, I hold x fixed. So this is a constant. Function value at f minus the interpolation polynomial p in x. Then over wx. I assume x is different from the loops. So w at x is a non-zero number. Yeah, you plug in x in t, in t, in t, in t, because x different from the loops. So this product non-zero. So divided by a non-zero number. Okay. Because by assumption, function f is in this set. Function f is in this set n plus 1 ab. Function f can be taken derivative n m plus 1 times. Yeah, this guy can be taken derivative n plus 1 times. P, just a polynomial. It has any order derivative. And w of t, also a polynomial. It has any order of derivative. Lambda, constant. So therefore, we have phi also in this set. Also in this set. Okay. Note that phi, this function, has n plus 2 zeros. Yeah, this function here has n plus 2 zeros. X0 is locked. When you plug in x0 in t, you will see that phi, the value is 0. Yeah, try. Okay, plug in x0 in t. Phi x0. Phi definition is here. F x0 minus p x0 minus lambda w x0. Function value at x0 is y0 because p interpolation polynomial at x0 also y0, and lambda a constant. we hold x fixed. W of x0, plug in x0 in t, then the first factor is x0 minus x0, so also 0. So this is 0. So x0 is a root of this function. The second root is x1. Plug in x1 in t, you will see that the value of phi is 0, and so on. X2 also a 0, and xn also a 0. How many zeros here? N plus 1 zeros. One more. X is a 0. We hold x fixed. X is a 0 of this function. Let me compute its value at x0. Plug in x in t. Yeah, plug in x in t here. Then we get fx minus p of x. Now x is a constant. Minus lambda w wx. Wx. Now I claim that this the right side, yeah, this expression is 0. How to see? Let me see. Fx minus px. We need to recall the definition of lambda. Lambda is here. So lambda is fx minus p of x, then over times w at x. W at x, non-zero number. X is different from the root, from the root. So w of x non-zero. Now I cancel this non-zero number. Then I get f of x minus p of x minus f of x minus p of x. So 0. So this function phi has n plus 2 different zeros, distinct zeros. Okay, by Rolle's theorem. Okay, now use Rolle's theorem. By Rolle's theorem, phi has n plus 2 distinct. Let me emphasize this. Okay, distinct zeros. Distinct zeros. Then first derivative has n plus 1 distinct zeros. Distinct zeros. And therefore, second derivative has n distinct zeros. Yeah, applied Rolle's theorem many times. Okay, and then finally, take derivative n plus 1 times. Here I make a mistake. Here this m should be n. Yeah, I need to change my notes. Okay, yeah, this m should be n. Okay, should be n. Repeat Rolle's theorem many times, then finally derivative on phi m plus 1 times has 1 0. below the 0 by, say, let me, below by sine x. Yeah, this side depends on x. Yeah, below. Okay. Okay, then let me compute derivative on sine m plus 1 times, then evaluate it at this point. Okay, take derivative on phi m plus 1 times. Here is phi, okay, the function phi. So we get f m plus 1 t, then minus polynomial m plus 1 times, and then minus lambda constant, omega m plus 1 times. Okay, then we get a p polynomial of degree n. A polynomial of degree n, take derivative n plus 1 times. It should be 0, right? Say, for example, polynomial of degree 1. Take derivative twice. 0. Take derivative twice, 0, right? Derivative twice is 0. If a polynomial degree 1, polynomial degree 2, take derivative 3 times. Derivative should be 0, right? First derivative, then the result is a polynomial of degree 1. Take the derivative again. Degree is 0. Derivative again 0. Yes, 0. Okay, so P, take derivative n plus 1 times 0. Then minus, how about W? W is also a polynomial. W, a polynomial, but degree n plus 1, n plus 1. The leading, if we multiply out this product, then the leading term is a t n plus 1, and then plus the terms with lower degrees. The leading term of this polynomial is n plus 1. Now take derivative n plus 1 times. Then the result is n plus 1 factorial. Yeah. This guy is this. Okay, now after I compute derivative on phi n plus 1 times, now plug in psi of x in t. Then we have n plus 1 psi of x is equal to f n plus 1 psi of x minus lambda n plus 1, n plus 1 factorial. Okay, now what is lambda? Go back to the definition of lambda. Lambda definition is here. Yeah, lambda is this number, f minus p over w. F of x minus p of x over W of X, then times N plus 1 factorial. Okay, now I rearrange the terms. Move this part to the left side. And then move this function value to the right side. Sine X minus actually this is a 0 because I assume derivative n plus 1, order n plus 1 on phi has 1 0. The 0 are denoted by psi x. So actually, this is a 0. So, okay, minus 0. Yeah, minus 0. Yeah, move this part to the left side. And the left side is 0. So we got this equation. Right. Now let me rewrite the equation. Then finish the proof of the theorem. It is a move W of X to the right side, N plus 1 factorial to the right side. Then we get this. Times Wx. What is Wx? Wx, let me go back to the definition of W. W is this. Now plug in X in T. Plug in X in T. Then we get product X minus the loops I from 0 to 1 to N. I from 0 to 1. Yeah. So this equation is the conclusion in the theorem. Yeah, is this equation. Is this equation. Yeah. So this section 6.1, two theorems. First theorem, guarantee interpolation polynomial exists. And also if the degree of the interpolation polynomial at most n, then the interpolation polynomial is unique. Theorem 1. Second theorem, present the error term to polynomial approximation of the function f. So this error term in structure very similar to the error term in Taylor's theorem.